So just a note from the last lecture. We were talking about dry friction. I drew this little picture. We have the normal reaction force and the friction force pointing up the hill. I wrote this equation without the magnitude, which doesn't make any sense because those are two vectors pointing in opposite directions, and it doesn't make sense for less than or equal. It's the magnitude. The magnitude of the friction force has to be less than a friction coefficient times the magnitude of the normal force, and then you can see from the triangle that that just becomes a condition on the angle of the slope, right? Okay, so we've talked about gravity, we've talked about drag and friction a little bit. The other force that will be one that we do quite a lot within this course is a spring force. And for the most part, we'll work with so-called Hooke's law. So my picture is I have, let's put, say, a wall here, a spring here, and say a little mass there. And I want to imagine is that in the rest state, let's suppose that the spring has length little l. Okay? So we say consider a particle mass m attached to a spring with rest length little l. Okay, so we can imagine our experiment is I pull the spring or I push the spring, so I move it from its rest state. Let's line this up, so that's the rest length. Maybe I pull the spring. And now I'm going to let go. So I'm going to, let's define this as x of 0. So now I let go, and of course we know what happens. Spring goes back and forth. So our final picture. Spring is going back and forth, and we'll call, at any given time, let's define its position by x of t. Okay. So, I'm going to describe that motion, and we need to say what is the force that the spring is applying to the mass. So in this idealization, the spring is sort of not having any mass at all. We're not actually doing the force balance of the spring. You can do that. It's more complicated. We're just saying that the force is really just a mass there, and the spring is applying a force to that mass. And it was Robert Hooke at Oxford in 17th century took springs and applied different weights to them and then measured how much they deformed for different weights. So he was changing the force he was applying and saw how that correlated with the deformation of the spring and observed that there was a linear relation. Okay, so the more force, double the force, you double the deformation of the spring. And this is what became Hooke's law. So if the spring is at length x. So generic x not equal to L, could be equal to L. The particle experiences a force, which we call the spring force, and, well, let's write it as a vector. F is some constant k with a minus, x minus L Ex. So in my picture, clear, I'm defining that as the positive x-axis, so that's the Ex direction. This is all one-dimensional the way I've drawn it here. Indeed, a spring force is always going to be in the direction of the spring. So if you want to think about the generalization of this, which we'll do in some instances, that vector should be the vector pointing in the direction of the spring, right? And what does this say? X minus L is how much I've displaced the spring from its rest state. Proportional, this is some constant k, called the spring constant. Positive. And the minus, I think rather than try to memorize whether there's a minus there or not, you just give yourself a simple thought experiment. Say, if I pull the spring, take x to be greater than L, what happens? The spring is trying to pull the mass in the opposite direction, which is the minus Es direction. Whereas if I compress the spring, x less than L, the spring pushing it to the positive Ex direction. Okay? And that's generically going to be the case. Okay, so simple enough. Let's think about the trajectory. And by trajectory, I just mean what is the motion of this mass? X of t. This pen is dying. Okay, so we write down Newton's second law. M and, okay. As a kind of rule of thumb, I think it's good to get in the habit of, when you're writing down Newton's second law, you keep in mind it's a vector equation. If the problem is clearly sort of one-dimensional, okay, it becomes a scalar equation, but what we're really doing is taking the vector equation and taking that component of it, right? So this is the sort of Ex component. So I could say that my r position vector is x of t Ex. F is the force I've written up there. So Newton's second law is the scalar equation m x dot dot is this force minus k x minus L. Now I need to give some initial conditions and my thought experiment. I pulled the spring to be, say, greater than L. So x of 0 is, say, L plus d. So d is how much d could be negative, how much I've displaced the spring. And if I pull it and let go, my initial velocity is what? 0. So x dot of 0 is 0. Okay. This is not a hard system to integrate, but sometimes we can make it even easier. And what's slightly annoying is that this is sort of there's that L term sitting over there. So the easiest thing to do, I think, is to define a variable which is just that distance from L. So if I define y of t to be x of t minus L, so that's the actual displacement of the spring. my logic there is that I'm just shifting y dot dot is x dot dot, but that x minus L just becomes a y, so it becomes a homogeneous equation. Yeah. So we get m y dot dot equals minus k y, y of 0, it's just the d, y dot of 0, 0. Probably you recognize that. Give a simple harmonic motion. Y is just sines and cosines. And that won't do that slowly, but you see that if you apply those initial conditions, you just end up with, well, okay. So that has solution y of t is a cosine omega t plus b sine omega t, where omega is defined as the square root of k over m. As a quick aside, what are the units of omega? Yeah. Now there's two ways you could get that. You could say, okay, I could work out the units of k, and to get the units of k, I need to think that kx minus L has to have units of a force, so that's a mass times an acceleration, and it's already got a length in there. So I could work out the units of k that way, and then divide out the m. I'm guessing that's not what you did. What's the quick way to know what the units of that are is that it's sitting inside a cosine and a sine multiplying a time t. So it has to have units of 1 over t. Right? And that is indeed the frequency, the natural frequency of the spring. So the units omega 1 over time. I think. Right, and then if I apply those initial conditions, I get that A is D, B is 0. Okay. Not surprising. My spring is simply oscillating. And there's no drag in this, so it never stops oscillating. Right? Hooke's law, called a law, as if it's sort of a feature of the universe. It's certainly not. It's an empirical observation that holds in the limit of small displacement, right? This linearity. So what a real spring does, if this is the F, the magnitude of the force, and this is the displacement, if I have a real spring, it's not, I can't extend it infinitely long by just increasing the force, right? And likewise, if I compress the spring, there's kind of a hard limit because I can't compress the spring smaller than length L. So a real spring is doing something more like, if this is minus L, there's kind of a hard limit where the force becomes infinite as I get close to that. It does pass through 0, and then normally a spring is, there are different kinds of materials, but a typical spring is then doing something like that, where again, as I get further stretching the spring, in order to stretch the spring a little bit more, I have to add more and more force, right? And of course, the spring shatters, fractures at some point. So Hooke's law is really the linearization of that nonlinear relationship, should be that slope. So that's Hooke, and this is sort of a nonlinear spring. What does a real spring do? It doesn't just oscillate forever. So if I add drag to the system, Okay, we said there are kind of two types of drag. For a spring, actually, it's quite realistic to add just a damping force, which would be something like Fd equals so linear force like that. Again, when you're trying to like create this force, you think to yourself, if x dot is positive, the force is acting the other way. So I need a minus there. Okay. And yeah, we use the linear one, which means we can do the maths pretty easily. So our equation becomes m y dot dot. In fact, if I put these forces all on the other side, we get plus b, sorry, well, yeah, if I do it with y, plus b y dot plus k y equals 0. And the addition of that means that we have two possible scenarios, depending on b squared minus m times k, characteristic equation. But in any case, it kind of does intuitively what we expect, that it doesn't oscillate forever, but the oscillations die out. And the two scenarios are if b squared minus m km is positive, then we have purely exponential solutions, which means I started my spring from some displacement, and it simply died out very quickly. That's t, that's y. Which is a spring that is, B is large in this scenario, so it's highly damped. I pulled the spring and it just sort of settled back. Or if B squared minus Km negative, we get sines and cosines with a negative exponential out front, and that is like damped oscillations like that. Okay. So for the most part in this course, these are the kind of forces that we'll play with: gravity, springs. Damping, actually, for the most part, we're going to ignore because sometimes it makes the nice mathematics a bit less nice, so we'll see in a few minutes. One other force that we'll at least mention, just to have another example, is from electromagnetism. If I have a charged particle, in an electric magnetic field, so we consider a particle with mass m, charge q, and velocity v. And the statement, which we're basically just going to take as fact, is that that experiences a force called the Lorentz force, which is Q E. E is the magnetic field, a minute, plus Q V cross B. So in the presence of an electric field E and magnetic field B. If you've not done any electromagnetism, this is probably quite harder to think about intuitively. QE, maybe not so bad. I have an electric field. The charged particle is feeling a force along the field lines. And if it's also moving and there's a magnetic field, you get a force orthogonal to both the magnetic field and the current velocity. So this was observed by Lorentz with various experiments and became sort of a fundamental principle from Einstein's relativity. For us, let's just take that as that's an equation, and it's another example where we can play with dynamics of motion. And a slightly tricky one, because there's a v, which is the velocity of the particle, r dot, living inside the force, but inside a cross product. So that can make things tricky. We won't do very much with this, but let's do an example here, and there's another example in problem sheet. So let's suppose we have a constant magnetic field, and I'm going to take things simple and say no electric field, and let's just find the trajectory of a particle in a constant magnetic field B. Okay. So I have my F is a Q V cross B, which is an R dot cross B. And to get things to work nicely, we're going to play one of these without loss of generality tricks. B is constant and arbitrary. So let's choose B to align with the z-axis, say. So a couple of things I can do without loss of generality. I can start the particle at the origin. So I shift my origin to wherever the particle was at t0. R of 0 be the origin. I'm going to let B be scalar B Ez. I think that's what I want to do. Yeah, this way. I also have an initial velocity. Am I out of generality? Can I do anything to the initial velocity? Yeah. Okay. Okay. Yeah, so you say I have an arbitrary initial velocity, and I've already fixed the z to align with B, so I can't do anything about that. But I can still rotate about z, and I'm going to rotate about z so that the xy component of that initial velocity only has an x. And hopefully it's the same thing we did the other day with the trajectory of the parabola. Right? I'm doing three things. I'm moving my origin, I'm aligning it, and I'm also rotating it. I do those three things without loss of generality. And of course, it's going to make the algebra much simpler. So it is worth pausing and thinking what's the most you can get away with. So I'll let r dot of 0. This one I'm just going to write it as, say, v1 in the x, nothing in the y, and a v3 in the z. Okay, so I'm leaving its magnitude arbitrary and the v1 components in the x and z arbitrary. Okay, so this is a funny looking equation. r dot living inside the cross product. On the other hand, b is constant, so I can actually just integrate that equation one time. mr dot is q r cross b plus a constant vector. And that constant vector, when I take t equals 0, that goes away. That becomes m times v. Let's call this v. If you're a bit worried whether you can do that through the cross product, just think about going the other way. Take a derivative of this equation. That's constant. The derivative just sees each bit of the r, becomes an r dot cross b. Okay. So I can integrate once. Now that's a bit funny because now the r is living inside the cross product. And now I think I need to go to components. So in components, I have m times x dot y dot z dot equals, and if I write out that cross product, I get qb. So that's x, y, z cross 0, 0, b. Gives me a y minus x 0, and then plus m v1 0 v3. So the x's and the y's are coupled to each other, but the z is living down here separate. So I can just integrate the z equation. So mz dot is just mv3, so z is just v3 times t, plus a constant of integration, which is 0 by the initial condition. And the x and the y, so we get x dot is, I'm going to divide everything by m, so I get, I'm going to define it as omega y plus v1, where omega is just qb over m. And I have y dot is minus omega x, like that. Different ways to solve that equation. Maybe the easiest, or I don't know, one of the ways to solve that equation is to observe that if I take another derivative of the top one, x dot dot gives me a y dot, and y dot returns an x. So I decouple them, I get a second order equation just for x, and indeed it looks like simple harmonic motion in the x. So I take a second derivative, x dot dot, omega y dot, which is minus omega x, so I get an omega squared. So I get minus omega squared x, which means x is sines and cosines of omega t. And indeed, if I use the initial condition that x dot of 0 is v1 and x of 0 is 0, I can get that exactly as x of t is v1 over omega sine omega t. And same as before, that omega must have units of 1 over time, and that's the frequency. And once you've got x, you can solve for y either by integrating that or just writing it out in terms of x dot, and you get y of t is, if I do a couple of steps in one, I get v1 over omega cosine omega t minus 1. What is the path here? What is the shape of this, the trajectory? It's like, yeah, so we're in the x and the y, we're just circling around, and in the z, we're moving, well, up or down, constant rate. This omega, this is not a super exciting trajectory, but this omega is called the cyclotron frequency. Cyclotron, I think. And the reason, you'll do this in problem sheet 2, I think, is that if you solve this same problem but you bring back a constant electric field, then what you find is that that Z starts accelerating. So you get sort of a similar motion where it's a helix, actually it's now spiraling out or in, but the motion in the Z direction is constantly accelerating. So this is like what is the idea of a particle accelerator. Okay. Good. I think that's all I want to say about that kind of force for now. Questions there? So what I want to do, this is moving on to part 3 or chapter 3 in the notes. Is to think about motion strictly in one dimension. But what I really want to do is start to make connections between Newton's second law and energy. There's both deep physical connections between Newton's sort of force balance and energy, and very nice mathematical connections as well. And so what we're trying to do is build some intuition, see how I can answer the same kind of question from an energy perspective or from a force balance perspective, but again, build it up mathematically where we don't take any assumptions other than sort of Newton's laws plus some new definitions, right? And we're going to start in one dimension where it's nice and easy to make sense of, and then later we'll see the same things in 3 dimensions. Okay, so we need to talk about energy. And the key is that there are 2 different kinds of energy. One called kinetic energy, the energy of motion. Kinetic energy of a point particle So because I'm in one dimension, I'm not going to have vectors for a bit. So x is just a single component in the one dimension. 1/2 m times x dot squared. So x dot is the velocity squared times the mass times 1/2. Energy of motion, that's clear because if I have no motion, x dot is 0, I have no kinetic energy. Right? And the other type is potential energy. Or what you can intuitively think of as stored energy. And we're going to define this in terms of a force. So the potential energy of a particle under a force f of x okay, we call it v of x, capital V, it's, okay, a little bit funny here. So it's minus the integral of f from, this is an arbitrary starting point, up to x of f of s ds. So it means roughly the potential energy is minus the antiderivative of the force. And we're going to try to make sense of why that's the sensible thing to have, both in terms of the minus and the antiderivative. So, of course, we can note that v prime of x is minus f of x. Okay, let's make a couple notes here. Nope. So one, which is obvious, is if that I have no force, if there are no forces acting on a particle, then there is no potential energy. Right? Two is a bit more fundamentally important, that V requires, this definition requires that my force is of a particular nature, namely that F is only a function of x, as in not also a function of x dot or other derivatives. So, for example, that doesn't mean that this couldn't potentially depend on, say, t as a separate thing. It's possible, but definitely not having x dots in there. And what am I saying? What kind of forces am I thinking about if I make this statement? Of the ones we've talked about, which ones am I discounting? Okay, so the magnetic bit of the Lorentz force, yeah, it's got the r dot. Think more intuitively, drag. And there's kind of a deep fundamental reason why everything we're going to do now does not work, or does not work nicely, if we have drag. We'll see that in a moment. So not including drag, friction, etc. And such forces are called conservative forces. And the reason for the name conservative force will become apparent in about a couple of minutes, because this is forces for which energy is conserved. Okay. This is not right. Every force that we experience, there is drag and friction. But let's do the mathematics without such forces, because there's very nice ideas, and then you can always think, how would this change if I add some friction on top of that? Another note is that x naught v is only defined up to a constant. Effectively, it doesn't matter. That x naught, it's only changes in potential energy that matter, so the constant is arbitrary. I've already noted that v prime is minus f. If we think about units for a moment, I'm calling v and t both energies, so they should have the same units. If we think about the units of, okay, this is a awkward notation because I'm using capital T for my fundamental unit of time, and I also have capital T as the kinetic energy. So bear with me for this awkwardness. I mean the units of the kinetic energy must be the same as the units of mass times I've got a velocity, which is a length per time squared. So I get a mass times the length per time squared. Very ugly. I'm using T again there. I apologize. Sometimes T you use capital K for kinetic energy, but we'll stick with capital T. Mass times the length per time squared, which is the same as, note, a mass times a length per time squared, which is a force, times an extra length. So that's a force times a length. And the typical unit energy is a joule, which is a kilogram, which is a Newton meter. Newton times a meter, so that's a kilogram meter per second, meter squared per second squared. And you can work it out that, of course, in fact, it's a bit easier to see the units from the V definition because I'm taking a force. Integrating means multiplying by a length. I get a force times a length. Of course, V has the same units. Okay, so one other key concept is the work. And we say is that the work done by a force f of x and moving let's say our particle from x1 to x2 is capital W. It's the integral of f from x1 to x2. And I can write that in terms of V. So that's minus the integral of dv ds from x1 to x2, which means W is V of x1 minus V of x2. Okay, so let's start to build some intuition on that kind of relationship. So I imagine, for instance, that I have define that as the x-axis, and I have a particle sitting at x1 under gravity, so gravity is pointing that way, and then say the particle moves down to x2. Okay, so if gravity, in this picture, gravity, the force is minus mg, constant, which means that V, the antiderivative, minus antiderivative, is mgx. And already you start to get a little bit of intuition for potential energy. It says is that under this constant gravitational field, it's a stored energy. The pen right now has lower potential energy, gravitational potential energy, than up here. Right? I'm sort of adding energy by bringing it up to here. Okay? Put in this kind of language, we see that V of x2 is less than V of x1, or V of x1 is greater than V of x2, which means that W, the work, let's suppose I've moved the particle from here to here, the work that I've done in moving it is V of x1 minus V of x2 is positive. And that number, that value, W, is the work done by gravity in moving the particle. Now, what has gravity done? It's moved the particle from a state of higher stored energy to a state of lower stored energy. But if the stored energy went down, the natural question is, where did that energy go, right? I have less potential energy in state x2. Where is that energy gone? Maybe you have a sense. It's motion, right? What's happened? The particle has moved. And so the kind of fundamental principle is conservation of energy. So what we say is that the total energy we'll call it capital E, the sum of T plus V, is conserved. And what do we mean by conserved? We mean through the motion of the particle, E is constant, E dot equals 0. Let's not just take that as a fact. We can actually deduce this from Newton's second law. So there's various ways to prove this. This is kind of a simple one. If I start from Newton's second law, which says that m in this 1D setting, you can do this in 3D as well. We'll do that later. mx dot dot is f of x. I want to take that equation and multiply both sides by an x dot. And now I'm going to recognize that the left-hand side is d dt of x dot squared, 1/2. And the right-hand side is d dt of v of x, because v is minus d dt of vx, because v is the antiderivative of f, and I've pulled an x dot through the chain rule. So that's the same as d dt of 1/2 m x dot squared, and now I'm going to bring the minus v over to the left, plus v of x equals 0. But what is that? That's the statement that d dt of t plus v is 0. That's the total energy. And we get this statement that t plus v is constant. Okay, let's go back to this falling particle and see if we can make some more sense of it. And so now I'm going to bring in time. I'm going to say that particle was at x1, it moved to x2. There's a motion from x1 to x2. So we have x of t1 is x1. So I say at time t1, the particle was there. Particle fell down to here, so x at some later time t2 is x2. And conservation of energy says that the sum of t of, how do I want to write it? The total energy at time t1 must be the same as the total energy at time t2. Okay, that's slightly sloppy because t is not x, but x dot. But nevertheless, we're saying the total kinetic energy at time t1 plus the total kinetic energy at time t1 must be the same sum at time t2, right? So that means that if I write that in terms of w, remember, was v of x1 minus v of x2 is therefore t of x2 minus t of x1. W is positive because it moved down, and that loss of potential energy is exactly the same as a gain in kinetic energy. This is t of x2 minus, t of x2 minus t of x1. So therefore, we can say that the work that was done by gravity in moving the particle to a state of lower potential energy is exactly the change, the increase in kinetic energy. The work done by the force is the change in kinetic energy. Which is exactly the experience intuitively, right? I'm holding the pen up high. It's got more kinetic energy, more potential energy. I let it drop. I look at this point right here. It had less potential energy, but it's moving faster. So the loss of potential energy is the gain in kinetic energy, energy of motion. So it gives us a way to think about this constant balance, just interchange of energy from motion to stored, t plus v. T goes up, v goes down, and vice versa. Okay. So let's stop there, and we'll look at some more specific examples on next class. Shall we get going? So as a quick recap of what we've looked at last time, motion in one dimension. So mx dot dot is f of x, a force, conservative force, depending only on the position x of t. And our energy formulation ends up as 1/2 mx dot squared, which is kinetic energy, plus v of x minus the antiderivative of f is the stored potential energy. And we showed somewhere around the end of the last lecture that the sum of those is constant under that form of Newton's law. We also defined the work as the integral of the force, though we'll probably make less use of that. Right, so let's look at some examples of how thinking about the energy formulation can be quite useful. So, let's suppose simple experiment. I throw a ball in the air. Say starting from x equals 0 with some velocity v, okay, just straight up. All right. Okay, so we sort of know the trajectory x of t is going up and then is coming back down if I'm just under gravitational field. And let's suppose I want to ask the question, what is the maximum height the ball reaches? So on the one hand, we know how to do that. I can solve Newton's equation. I can just work it out algebraically, or I can look at when x dot equals 0 at the top. But I can also do this entirely from the energy formulation. And so what I would do is I would say the total energy E, which is constant, is, I have over there, 1/2 the velocity, mass times velocity squared plus v. V of x is minus mgx, right? So I get 1/2 mx of 0 dot squared plus v of 0. So in other words, if it's constant, then that constant is whatever value the kinetic and potential energies have at time 0, which is like that. And v here, capital V, sorry, we shouldn't use, that's maybe a bad choice there. Let's just call that x dot of 0, so I'm not double using v. V is V is mgx. So that's 0 at time 0 if I'm setting it up this way. So therefore E is exactly 1/2 m x dot 0 squared. And what is special about the maximum height? We sort of say what's happening in motion is potential energy is being converted to kinetic energy, and then it's being converted back to potential energy, right? Always the sum of them being the same. So I started with no potential energy and lots of kinetic energy. And as the ball goes up, it's losing kinetic energy and gaining potential energy, right? And the maximum height is the specific point where all of the energy has been converted to potential energy. So at this point, at max height, the energy is entirely potential energy. So mg times, we call that, say, x max. There's nothing there, everything's there, is equal to E. Right? So without solving anything from Newton, I get a formula for the maximum height as, because I have E, 1/2 mx0 x dot of 0 squared, I get a formula for x max. Okay. Okay, let's think about another example. How about a spring? So we've said, I think the last lecture, that spring force in this 1D motion looks like that, minus k times x minus L, L being the rest length. So if x is greater than L, spring force acts in the minus x direction, and the constant k converts it to a force. Yeah. So for the spring force, the potential energy, V, antiderivative of that is like an x minus L squared over 2, and I get a minus, cancels out the minus. It's k over 2. X minus L squared. Okay. And as we know, right, so just to maybe redraw that picture, there's my spring at rest, length L, and my experiment is I pull the spring and then let go. And we know the motion of the spring, x of t, if that's my experiment, well, it's okay, I'm going to draw this in a slightly funny way. It's oscillating around x equals L, so I'm going to make this axis actually x equals L, otherwise we can define y as x minus L. It's oscillating around that point, and we just get a smooth oscillation like that. Okay, that's the picture we had before. Where's this energy exchange in that picture? Where is the kinetic energy maximum? And where's the potential energy maximum? So here, and here, what's happening?
At the maximum, it's like all potential.
It's all potential energy. Yeah. So I pulled the spring at that point. It's all potential energy. I let it go. It starts converting. Right here, the spring doesn't just stop. This is an equilibrium position, right? It's at its rest length. Why doesn't the spring stop? Because it's got this whole load of kinetic energy which just pushes it straight through the equilibrium to a state of, again, potential energy the other way, compressed. And now it's got lots of potential energy here, but no kinetic energy, goes back the other way, gets pushed right past its equilibrium because it's got all this kinetic energy, and so on and so on. Okay? So we want to label these points. At these points here, we have T is 0. T is our kinetic energy diffused, and V is max. And likewise, I don't have to do any calculation at these points. V is 0, and therefore T must be max. Let's consider for a moment, this is kind of a nice mathematical picture, this switching back and forth between kinetic and potential. Real springs don't act like that, right? What does a real spring do? Real spring has some drag. If I just think about Newton's law, my F is now like a minus K x minus L. That's the simplest version, minus Bx dot. How does that picture change if I have that extra term there? You can see that that second line is not true anymore. Right? I can't get to that second line because I can't integrate F. Can't find an antiderivative. Because we still kind of understand, right? If I solve Newton's law, I don't get that shape, I get that shape with a decaying amplitude. So what's actually happening? So energy is not being conserved here. Energy is being lost as the decay in amplitude is a decay in potential energy, at least decay in spring energy, right? Then you might ask, well, is that right? So this is how a real spring behaves, and you see energy is not conserved. But that's not quite right either, because energy is conserved. Where did that energy go? So this energy was being lost from the spring, but did it vanish? Sort of. You think about it, if I have a spring in this room and I pull the spring and let it go, the spring has to move the air out of the way, and to move the air out of the way, it gives the air particles a little bit of energy, right? They jiggle a little bit faster, which is what we measure as heat. And of course, those air particles right next to the spring, then they jiggle the air particles next to them a little bit more, and next to them. So the energy of the spring is being conserved, but the total energy is being conserved, but in a very complicated way that would be hard for us to track down. If I really have a spring in this classroom, the spring would stop oscillating and the temperature in the classroom would go up by some immeasurable amount, right? So those are kind of hard details for us to keep track of. So when we're thinking about it mathematically, we kind of prefer that spring and conservation. Okay. So I want to talk a bit more generically now. And this kind of picture gives us a nice way to understand motion, which is in terms of what we'll call an energy landscape. Okay, so the idea is that if you tell me the shape of the potential energy, V of x, then I can reason the motion, right? So the idea is that the shape of V, we call the energy landscape, the shape of V gives us the possible motion. Okay. So, in fact, just doing our spring example again. So V is K over 2x minus L squared. So now I want to plot V as a function of x, and it's just a parabola centered around x equals L. And let's suppose we try to imagine this experiment entirely in terms of that picture. Okay? So my experiment is I take x and I pull it to some value greater than L, and let's call that this point right here x1. Actually, move it a little further over. Say here. Okay? And I let go. So the total energy in the system is exactly this value. Draw a horizontal line here. This is E. Is V of x1. Okay, so if I start the system, and we need to be clear, I'm starting with no velocity. If I start with velocity, the picture gets a bit more complicated. But if I start the system at x1 with no velocity, what happens? In other words, how do we see that picture, that motion, entirely in terms of thinking about the property of V? Well, one thing you can do is say at the very beginning, if I'm unsure, at the very beginning, mx dot dot is f of x, and f of x is minus v prime, and at that point v prime is positive, so minus v prime is negative, so therefore the particle begins accelerating to the left, right? And which is negative at x equals x1, implies we start accelerating and the picture you might well have in your head is that I have like a ball rolling in this hill on like a frictionless surface that has that shape of hill. And if there's no friction, what is that ball going to do? It's going to roll down, it's going to roll up the other side. And we kind of intuitively know that what happens is the ball rolls up to the same height and then it rolls back down. But let's convince ourselves that that's what must happen. So by the same kind of logic here, when x gets to L, V is 0 and the energy is entirely kinetic and it's going to the left. When x gets to this other point over here, so call that x2, at x equals x2, forget about springs, that's just a shape of a v of x. At x equals x2, E is v, right? Because v is at the value it started at, which means the energy is entirely v, which means x dot must be 0. So you can write it that way, right? E is v, which is v of x2, because that's v of x1. And therefore, at x2, it must be the case that x dot equals 0 at that point. So now the object has stopped, and we kind of imagine that it's going to go back the other way, but why must it go back the other way? Why not just hang out right there at x2? we can come back to this argument. Now mx dot dot, which is minus v prime, is positive because I'm on the other side and the slope is the other way. V prime is negative, so mx dot dot is positive, which means it starts accelerating back to the right. And on and on, right? That motion continues forever because we just loop that argument. Gets back to x1, all the energy is kinetic, x dot is 0, acceleration goes to the left, so on. Okay? Okay, that's quite a simple picture, but we can make these same kinds of arguments for a more complicated landscape. So let's just make one up. Suppose v of x has this kind of shape. And by the way, you also see in these pictures why this constant, I said v is only ever defined within a constant because it's the antiderivative. Why does that constant make no difference whatsoever? I can shift that curve up and down and the arguments don't change, right? So let's draw a v, and I'm going to make it a little more interesting. So it's going to go down, up, down, and maybe off to infinity, okay? And that's x. And of course, if I restrict to staying in there, it's the same basic picture, but there's kind of an interesting thing that might happen, which is based on that critical point there. And so if I label this point as, let's call that x, xe, there's an equilibrium. We'll talk more about that detail in a moment. Then what I can do is think about the energy there, and I can draw this horizontal line over here, and then there's this special point over here, which I might call x star. That's supposed to be horizontal. Okay. And now the question is, suppose I start the system at some value less than x star, and I let go with 0 velocity. So if x of 0 is less than x star with x dot of 0 equals 0, then the total energy in the system is greater than the energy at xe. So what happens? Let's not argue, we sort of know what happens just thinking about a ball, but let's argue in the kind of way I've done up there. I let it go, starts accelerating to the right. It's going to keep accelerating to the right as long as v stays positive, right? Because it's only when v goes to 0 that everything needs to switch to kinetic energy. So I get to xe, I get all the way up to xe, and e is greater than v of xe, which means I still have a little bit of energy, which means I still have a little bit of kinetic energy, and I just keep going over the hill. So e is greater than v of xe, which implies that x dot is greater than 0 at x equals xe, which implies that the particle goes over the hill. The different scenarios we consider, suppose x of 0 is exactly xe, x star and x dot of 0 is 0. Okay, you kind of imagine that, well, I don't know, you want to take a guess at what would happen in that scenario? Okay, so you've given it just enough energy to get up that hill, and when it gets to that spot at the top of the hill, well, there's a question of does it get to that spot at the top of the hill? You're going to do that in one of the problem sheets. But even if it did get to that spot at the top of the hill, it has no energy. The slope is 0, so it doesn't have the same feature of wanting to accelerate back to the left. Okay. x dot of 0 is 0. And let's just convince ourselves, if I start at xe, what happens? I'm going to say nothing, right? I'm at the top of the hill, and I'm just sitting there. Intuitively, that's clear. Mathematically, what's the argument? So I'm at xe. I need to kind of play this game of connecting slopes of v to accelerations. mx dot dot is the slope of v, and the slope of v is 0, so there's no acceleration at that point. There's no acceleration, there's no velocity, it sits still. And of course, there's lots of other scenarios we might imagine. For instance, suppose I start a little bit to the right of x star, and I ask the question, I want to go over the hill, so I need to, if I just let the particle go, it's not going to go over the hill, it's just going to do that. How much velocity do I need to give the particle to make it over the hill? Do we have enough to work that kind of question out? Yeah. Okay, so we look at the difference between the potential energy from where we started and the potential energy of where the hill, at the top of the hill is, and we need to make up that difference with kinetic energy. Exactly. So we can work all these kinds of scenarios out. Another thing we can do, we can ask questions about time. So time is kind of lost. The variable time is sort of lost in this picture, but it's not completely lost. And indeed, for a generic v of x, we can compute the time that the object requires to get from one point to another. So the idea is 1/2 mx dot squared plus v is constant, so the x dot has a d dt in it, and if I think about separating that, I can bring time back in. So 1/2 mx dot squared plus v of x is e. If I write that as a dx dt squared and I solve for dx dt, I get dx dt is, there's a plus or minus root 2 over m times a square root of e, which is constant, minus v of x. Okay, that's a little bit ugly, but on the other hand, this only depends on x, so if I divide this square root over here and put the dt over there, then I can integrate. I get a t on the right-hand side and whatever this ugly integral is on the left. So I have a formula, t is integral, plus or minus root 2 over m. Okay, I'll do this in One way to do it is leave this generic as an antiderivative. The antiderivative of dx over root e minus v of x. And let's suppose that I could solve that integral. Oh, this should be m over 2 this way, right? In principle, if I integrate that, I'm saying suppose I could, then I would have t of x. And suppose that I could then invert that relation, then I get x of t. Okay, it's not a very nice exercise, and it, you have to be very careful about the square roots and even the plus minuses, but okay. That's at least in principle something we could do. And just to show you an example that it does work, if I go back to my spring, and I'm going to make the calculation simpler by taking L equals 0, so rest length is 0. So V is k over 2 times x squared. This is a spring that wants to be 0 length. So on the one hand, if I solve Newton, mx dot dot is minus kx, and I'm going to think of a generic, without putting generic solution, no initial conditions. Then I get x. I'm going to write it that way, so this omega is the square root of k over m. I've done a little trick here, and it's a nice one to observe because it can be quite useful. So the solution of that is sines and cosines of omega t. Yeah. Sometimes it's nice to smush those into a single cosine where my two arbitrary constants are something sitting out front and an arbitrary phase. You can always do this. And if you're not convinced, expand that cosine of a sum to be a cosine and a sine, and you see that it's an arbitrary thing times a cosine and an arbitrary thing times the sine. Okay? Sometimes it's nicer to only deal with the cosine and keep that second degree of freedom. We definitely need 2 degrees of freedom, but I can keep it inside the cosine. Okay, so that's the solution we all know how to work out. If I do this formula above, I get t is plus or minus the square root, the integral of dx over the square root. So I'm going to do a little bit of algebra here. So I'm going to pull an omega out front of the integral, and I'm going to write it as 2e over m omega squared minus x squared. So all I've done is taken that v, put it into there, and brought that m to make this omega, and then I've shuffled some things together so that I get a minus x squared here. It's nothing very fancy. That's not very nice, but we can integrate that. I'm thinking I need to use a trig identity. I've got a something squared minus something minus an x squared, so I want to use like a 1 minus cosine squared. So if I let x equal the square root of 2e over m omega squared cosine theta, then this becomes like a 1 minus cosine squared. That's good. That's a sine squared. A square root is a sine, and the dx is also a sine, so it's something I can integrate. So I get t, again, rushing the algebra a little bit, t equals minus plus 1 over omega. There was a dx became another minus. So then it's just an integral of d theta, which I can integrate, so I get something like t t minus a constant, let's call it t naught, equals minus plus theta over omega, and theta is the arc cosine of something with an x, right? Okay. And you can go one step further and then take, well, I mean, I guess you could have, yeah, so I can then take the cosine and I get back to a formula like that. X is the cosine of t. This is not a nice way to do it. This, just solving Newton's equation is much easier. This is partly to convince you that this idea of extracting time as something that involves the integral of a square root of the energy minus the potential energy is consistent. You might be a little worried about that minus plus. Any ideas why there's a minus plus there? It's coming from the x dot squared. Let's hold that thought for a moment. I want to ask a different kind of question. So this is not a nice way to solve this problem, but it's a nice way to talk about time. And a scenario where this is quite useful is the following. So let's do a plot, and I want to compare two thought experiments. So here's a V, and there's an X, and I'm going to make a similar kind of shape like that. And then we're going to take two different scenarios. So in scenario one, we have our object just kind of rolling in that nice gentle valley. Let's call that point x1, and we'll call that point x2. And scenario one is if I start at point x1, I know that the object, by our arguments, is going to make its way to x2. How long will it take to get there? So scenario one starts at x1 with x dot equals 0. How long to reach x2? And in particular, the kind of interesting question with, especially if it's a more complicated energy landscape, is does it reach that point in a finite amount of time, or does it take infinite amount of time, which it can? Intuitively seems like it should make it in a finite amount of time. It rolls down, it rolls up, right? But I'm not even telling you what V is. I just want to think about whether we can answer that question. So the total energy in the system is V of x1, which is V of x2, right? The time from our formula above, the time it takes to go from x1 to x2, is this integral. And now I want to write a direct integral. So not a generic antiderivative, but an integral from x1 to x2 of dx over the square root of e minus v of x. Now this is where you have to be a little bit careful, because you might say, oh, well, I know the particle is actually going to go to x2 and then it's going to come back to x1. And if I ask how long it takes to get back, you know, maybe I should just integrate from x1 to x1, but that looks like nonsense because I end up with 0. Right? So we need to make sure that we're integrating sort of a single path where x dot hasn't changed, right? Because that formula came from thinking about x dot and solving for it. the plus or minus is kind of related to the fact that there's a time reversibility. If I do the same thing going from x2 to x1, I get the same value. If I run my experiment backwards in time, I get the same answer, which is why there's a minus. For us, it's safe to just say, I'm interested in time going forward, I take the positive. So my question really is, for a given v and these choices of x1 and x3, does that integral converge? That's all I care about. I want to know, does it get there? I mean, how long means I need to solve the integral, but the broader question, is it finite, is the question of does that integral converge? Converge, that's not a very nice G. So one thing we can do is think about when the particle gets close to x2, I'm going to do like a Taylor series of this form around x2. So v of x2 is approximately, v of x is approximately v of x2 plus v prime of x2 times x minus x2 plus dot, dot, dot. So that's a Taylor series of the function v around x2, and I'm just keeping two terms at the moment. Which means that 1 over the square root of e minus v, well, e is v of x2. So in this expansion, that looks approximately like 1 over the square root of v prime of x2 times 1 over the square root of x minus x2. But in terms of an integral, I have like a 1 over square root of x integrated around x equals 0 is the basic form of that, 1 over integral x minus x2 around x2, which is a convergent integral. So this is integrable at x equals x2. Okay, actually, I've probably done this a bit. X is staying less than x2, so I should really have it as an x2 minus x. As I said, I'm not that concerned about integrating it exactly. I mean, I'm asking the question about whether I have a finite value or not. And that little expansion and ending up with a 1 over square root is a convergent integral, tells me that it reaches x2 in a finite amount of time. For a point of comparison, let's take a different experiment, which is this trying to get to the top of the hill. So call that point x3 and call that point x4. And now I ask the same question. I start at x3, let it go, and I ask, does it reach x4 in a finite amount of time? So, scenario 2, x of 0 is x3, x dot 0 is 0. Question is, do we reach x? And I make all the same arguments. I say, okay, take that integral with the e minus v, Taylor expand around x4. And what's different? Why is that kind of a special experiment? V prime of x4 is 0. So when I do this expansion, if I follow the same steps, v of x, so x close to x4, v of x is like v of x, v of x4, which is v of x2, which is e, plus v prime x4 x minus x4, but that's 0. So I need to go one term higher in my expansion. X minus x4 squared. And that changes everything, because now I integrate 1 over the square root of e minus v. The e minus v of x4 goes away, because that's how we've set up. E is v of x2, which is v of so the integral of 1 over x. I messed up my, what was I calling it? x3. x3 and x4, so this is a 3. This is a 3. This now looks like an integral that sees x4 of 1 over, well, x minus x4 squared inside a square root. So I get like, I get like a dx over x minus x4, which is not a convergent integral. So going one term higher in the expansion, change the entire sort of local nature of that integral. I'm being a bit sloppy here. There's extra constants that I don't really care about. The nature of the integral, finite or not finite, is coming from that x minus x4 integrated up to x4, which is divergent. Okay. So quite nice. We've done nothing with Newton. We've not really even said anything about the v. We just said v has these properties of going up, down, etc. And we can argue that that experiment takes infinite time to reach that point. Okay, quite nice. Right. Just to give you one more kind of one to think about. Let's suppose I have a similar experiment. And now I want to start my particle to the left of this point. Let's go like this. So this point here, call that x, I don't know, call that x1. And we've argued that if I start to the left of x1, with x dot equals 0, I go down, I go up, I still have a bit of energy, I go over the hill and off to infinity, right? We see, we've made that argument. X goes to infinity. Now the interesting question with a dynamic system, you can go to infinity in infinite time. You can also go to infinity in finite time. That's a finite time singularity, it's called. It's really important in dynamical systems. And that's a huge distinction. Going to infinity, I might just keep going, but take me infinite time. Diverge in finite time is a completely different behavior. So how do I think about that question? Do I make it to infinity in finite time or infinite time? What's going to determine that? We can set it up here. The time it's going to take me to get to infinity is this integral from x1 to infinity. So it's the properties of the v again. And I'm not going to say more about it. You can do different kinds of analysis, but now it's the question of whether this thing can converge or it can diverge, and it depends on the rate at which v itself is going to infinity. So you can work out polynomial form, critical point where that can be finite or it can be infinite. Okay. So I just want to get a hint of what we'll be doing next, which is still very much along these same lines, which is equilibrium points are points where the system is balanced. The forces are balanced. There's no acceleration. The interesting question is, if I'm close to an equilibrium, what happens? And this is called linear stability. Really a very fundamental idea in loads of fields of applied mathematics and some in pure mathematics as well. So here's the idea. Draw one more v. There's a v of x. And note, if I call that point x1 and I call that point x2, we observe that v prime of x1 equals v prime of x2 equals 0. And what does that mean? Means that f is 0 at those points. And if f is 0 at that point, then that means that if I start exactly at one of those points with no velocity, then nothing happens. x1 or 2 with x dot of 0, 0. For all time. You can just solve Newton's equation if you want. It has no force. There's no initial conditions. X is identically its initial value, x1 or x2. And such a point is called an equilibrium point. Equilibrium really meaning that the forces in the system are all balanced, but we can also understand it from an energy landscape as the ball rolling in the hill. I'm either at the bottom of a valley or the very top of a hill. Of course, fundamentally, we understand that the behavior is not the same at the bottom and the top. If I nudge the ball from the top, it goes down the hill. If I nudge the ball from the bottom, it just does a gentle oscillation. Right? So the question is, how do we classify the behavior if I'm close to such an equilibrium? So our goal is to describe / classify and what does close to equilibrium mean? It might mean that I start at that point and I give it a little velocity, or maybe a nicer way to do it is to start, for example, x of 0 equals x1 plus some epsilon small. And maybe still with x naught of 0, 0. And what we'll do the next time is formalize this kind of mathematics of answering that question, what happens? And the big classification is what we'll call stable, which means it stays close to the point, and unstable, which is the going over the hill, goes away from the point. So let's stop there. Thank you.